Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome to episode 63 of the Reliability Matters podcast. Today I'll be speaking with Doc Brown. Doc Brown brings his more than 30 years of electronics reliability experience to clients of Ansys. Prior to joining Ansys, he spent 20 years at Medtronic, where he most recently concentrated on cross-business unit implementation of reliability initiatives for Class 3 medical devices. He was also responsible for supplier assessment and approval, ongoing supplier audits, failure analysis, corrective actions, MRB, sampling, and ultimately full accountability for quality and reliability of commercial off-the-shelf and custom products and assemblies from a worldwide supplier base. Earlier in his career, Doc also spent time at Sundstrand Data, where he led the implementation of Boeing's Advanced Quality Systems program and with Olin Aerospace. As a volunteer, he has been involved with ASQ, IEEE, IPC, and SMTA. He was the keynote speaker at the SMTA Cleaning and Coating Conference and won the Best Paper Award at the SMTA Microelectronics Conference. He's taught on the subjects of design for reliability, tin whiskers, statistics, design of experiments, and contributed to standards development. Today's episode is a little different than others. Doc will be sharing a very interesting presentation on the subject of reliability. If you're listening to the audio-only version of this episode, you may want to view the video version so you could see Doc's slide deck. The video version of this episode and several others are available on the Reliability Matters YouTube channel. Now, here's my conversation with Doc Brown. Doc Brown, thanks for joining me today on Reliability Matters. I appreciate you being here.
Oh, Mike, it's really nice to be with you and have a chance to take this opportunity to share some lessons learned and lessons lost with the people that are coming up in this field behind me, the younger folks that are soon going to be taking over. Some months back, I heard somebody remark, the old saying, "You can't take it with you," and it had me kind of scratching my gray beard, saying, okay, but really you can take it with you. And that's the sad thing about being part of the silver tsunami, to use your phrase.
Which I stole from somebody else, by the way. So
okay,
we'll just keep passing it down.
The attributions for footnotes are lost.
Exactly.
So, once I do take a permanent retirement as opposed to my temporary retirement that I took in 2012. All the things that I've said and done are likely going to be lost in the dustbin of history. So that I can take with me. I don't want to. I want to share frequently and liberally, both inside my organization and outside the organization, with the volunteer work I've done with IEEE, SMTA, IPC, those kinds of organizations. So kind of like a longitudinal, career respective kind of thing. So if we could go to that first slide. So right now I am working as part of Ansys Corporation. Ansys acquired DFR Solutions about a year and a half ago. When that merger and acquisition activity came around, my wife kind of elbowed me a bit and says, "Hey, how many times have you been through this?" And so I had to count up on my fingers, and the answer was 9. So throughout my 40-plus year career, I've been through 9 merger and acquisition activities. And I have to say that the merger activity that Ansys and DFR Solutions did is far and away the best one I've ever experienced in my career. Those folks really knew what they were doing. They brought us all on board very quickly and crisply. Ansys has a wealth of resources that they made available to us, and it's been a really excellent organization to be associated with.
Doc,
for someone like myself,
I hope you don't mind if I interrupt. You mentioned 9 acquisitions. I've long said to my friends who are not in this industry that this industry is like a life sentence. You leave either in a casket or after winning the lottery, but you don't generally leave the industry. And when you go to trade shows, you see the same people standing in different booths with different badges, but it's the same people. It's a lifer. It's definitely a lifer.
So what that would say to the younger folks coming up in this business is that it's vitally important to you and to your career that you establish and maintain a good reputation. Because as you move through those kinds of life and career transitions, that's the one lasting, enduring legacy that you can hold on to, is that reputation. So don't squander it. So I've lived and worked in the Seattle area for the vast majority of my career. As a kid growing up, my dad was in the Army. We moved around a lot. I had the opportunity to learn a bunch of things from a bunch of different people, and start my reputation over again. If I messed up with a group, then 2 years later we'd move to a different town. We finally somewhat settled in the Seattle area in the early '60s, and at that time Boeing was very much the dominant employer in the area. So when I went into BSEE school in the late '60s, Boeing was going great guns. They had the 737, the 727, the 707. They were working on the 747, and things looked pretty good for all the engineering disciplines. And when I got out of BSEE school 4 years later, it was a dramatically different situation. One of the real estate agents here in the Seattle area actually put up a sign saying, "With the last person leaving Seattle, please turn out the lights." So when it came time for me to start interviewing for an engineering job, there weren't a lot of engineering jobs out there. My girlfriend's dad was a manager at the John Fluke Corporation, and he could not even get me a courtesy interview there at John Fluke. So there were no engineering jobs available anywhere. So it's very similar to the environment a lot of young people are facing these days, coming out of their educational process and looking for their first career. And so I had an opportunity through a friend of a friend of a friend kind of thing to start working for the local rocket engine manufacturer. And it was not an engineering position. It was not even a technician position. The position they had open was of an assembler. And so I took that and worked in that position for several months. Then a technician position opened up, and finally, about a year and a half later, an engineering position. So one of the things that they really emphasized with us in the rocket engine business is when you come across a problem or a shortcoming, when do you want to deal with that? And the catchphrase that has always stuck in my mind was, do you want to deal with it when the problem shows up or when it blows up? And in the case of the rocket engines, sometimes that blow up is literally true. So the photograph that we're looking at here is one of the premier rocket engines that the company that I worked at designed, developed, and sold to NASA to go on the 2 Viking Mars lander vehicles. It was a very interesting project. It was a non-standard configuration of nozzles. You can see there the nozzles of the rocket engine are very splayed out. And the reason for that was that the Viking Mars landers, unlike the subsequent Mars landers, had no ability to move. Once they were down, and that was it. So a standard rocket nozzle would have so eroded and displaced the soil structures that it would have compromised the science part of the mission. So the engineers and scientists there came out with that splayed rocket nozzle. There were 3 of these on the 3 corners of the Viking lander, and it was a fantastic success. There was a lot of good science, a lot of good pictures that came out of those 2 landers. So one of the things that I picked up on during the time I was working there was the concept of fitness for use, both in quality and reliability. And they emphasized 2 parts of that. That was the technical fitness for use, but also the business fitness for use. They had a really excellent program management office. And one of the things that they emphasized to us there was the concept of the launch window. So if you're trying to go to Mars, that launch window comes around about every 2.5 years. And that launch window is open for just a few weeks. So regardless of your technical proficiency, if you're not adept at the business part of that, if you can't create, assemble, test, and deliver that rocket engine on time or a little early, you might as well not done it at all, because you're going to miss that launch window, and your next opportunity is, as I said, going to come around in a couple, 2-3 years. So there was a lot of emphasis placed on that. So for those that aren't familiar with how the windshields on jet aircraft work, they're a very complicated structure. They're quite thick. They're a laminated structure of different glasses and different plastics and different adhesives, different metallizations. So there's metallizations that allow the window to be heated. Typically, this would be on a small business jet, about 1 kilowatt per window. On the larger commercial jets, they're about 2 kilowatts per window. There's a sensing wire that runs around the periphery of the window. And the company that I worked for also made electronics, avionics for commercial and military applications. And one of my first assignments as a young reliability engineer was to lead a failure modes and effects analysis, FMEA, to look at this particular piece of avionics, the windshield temperature controller. And what this controller did was it sensed the temperature of the window and then turned on a proportional voltage and current to those heating elements within the window to maintain a constant temperature of about 120 F. So this had the effect of both keeping the windshield defrosted, but also that was the point at which the window was the strongest. So even if you're on a terrestrial location on an airport, that window is still at 120 F. So we went through and we did all of that FMEA work to the requirements, and we think, okay, that's a good job. We got that all figured out. We did find a couple things. So it goes into production, goes into deployment. And a couple years later, there was a customer situation where the windshield cracked. And so we got the controller back to do a failure analysis on. And frankly, as the leader of that FMEA activity, I messed up and messed up severely. That was the closest thing I would ever care to come to for being responsible for a fatality. Fortunately, the windshield did hold in place. This is not a picture of that particular one. This is a picture that I grabbed off the internet. But you can see the fracture patterns. And had that window shattered and exploded, the results could have been catastrophic. So what went wrong with that failure modes effects analysis? So what I neglected to consider was what might happen as a consequence of a failure of a failure. And what I mean by that is there was a pulse transformer inside that windshield temperature controller that was activated by a power transistor. And we had looked carefully at that and what was going to happen, if that power transistor failed short or some component before that applied the power to the gate of that transistor, and all of the voltage and current was then applied to that pulse transformer. So what we did not consider was what might happen on the internals of that pulse transformer. And what ended up happening was the high temperature solder that made the connections internal melted and flowed out of that transformer enclosure and dribbled down over the circuit board and shorted the 208 volt, 400 hertz power to the sensing wire on the window. And when that happened, the window fractured. So that was, as I said, the closest I would ever care to come to being responsible for a fatality. So in terms of lessons learned, lessons lost, the takeaway from that is you really need to know all the physics and chemistry of what's going on, and look downstream at what the implications of those failures could be. The American humorist Will Rogers once remarked that it's not what we don't know that gets us into trouble, it's what we know that ain't so. And there's a couple things that I'd like to mention during our time together here today. One thing that we commonly say we know that isn't exactly so is high temperatures will increase failure rates. So you see a lot of testing activities designed to stimulate failures in electronics, and it's widely held that the higher the temperature, the higher the failure rate. That's true in a lot of cases, but not all. And we'll talk a little bit more about that in a few moments. The other one that I'd like to beat into submission and extinguish, that a lot of people still hold to, is that when you're soldering your circuit board, that your reflow profile, if you're using a no-clean process with a high solids flux, you need to activate that flux. And there's a lot more involved in the physics and chemistry there. And there's a lot more than just assuring that you have the right reflow profile. There was actually an incident that happened on this particular aircraft flight some years back where that windshield did pop out of the plane. And mercifully, there just happened to be a flight attendant standing by in the jump seat of the cockpit who reached forward and grabbed the ankles of the captain of the plane. This was a recreation that was done subsequent to that and was on public television. So as it happened, the co-pilot, the first officer, took over quickly and successfully landed the plane. The captain recovered after spending a period of time in the hospital and rehab, went back to work at British Airways, and finished out his career many years later at the mandatory retirement age. That could have been a lot less pleasant. Some years ago, I was at a technical conference, and Dr. George Box made a presentation there. And he was talking about some of his mathematical models. And somebody took him to task and said, Dr. Box, your model is wrong. You only included linear effects. You didn't include interactions or quadratic effects. And he kind of stroked his chin a bit and he says, yeah, you're right. But in essence, all models are wrong and some are useful. So what I'd like to share with you today is some models that I have found throughout my career to be quite useful. When I was working at one avionics manufacturer, I was put in charge of the Boeing D19000 program, which was the advanced quality and reliability system that Boeing was asking all of its suppliers to use so that they could qualify the 777 aircraft out of the gate as an extended twin operation aircraft. So they could fly that over the Pacific and Atlantic Oceans without having to go through a lengthy qualification process in production like the 57 and 67 Boeing aircraft did. So as part of my responsibilities there, I taught a bunch of statistics and statistical process control classes. The first couple classes I taught were to folks that were in the machinist and sheet metal shops, and they had a lot of trouble grasping what was going on with alpha beta risk and type 1, type 2 error and signals for activities on when SPC rules were violated. And so long about the time I was preparing for the third class, I realized that, these are real sharp, bright, motivated people. They work with math every single day. They're doing things in the machine shop down to precisions of 1/10 or 1,000, what they call 1/10, which was 1/10 of 1,000. So it was 10 thousandths of an inch. So really tight kinds of tolerances that they had to calculate out all the different ways that they could get there. Bottom line is, these were not dumb people. Who was dumb was me, the instructor. I hadn't done a sufficiently good enough job of explaining conceptually what was going on with these things. So I developed this risk assessment model. So, there might be some times where this model doesn't work, but I think this is one of those useful models. So it's a risk assessment model to help explain what's going on with those statistical types of errors. And fundamentally, what we're looking at here is when you're doing something with statistics, in essence, you are extracting from the information that you have at hand a perception or a belief, but underlying that is an objective reality, right? So one way to kind of look at this, most of us have had some kind of experience, either as a pedestrian or as a driver, where you come up to some kind of intersection and you're trying to make the decision, is it safe for me to go across? And what you're going to do is you're going to look at what's going on internally with your vehicle and yourself, what's going on externally, what kind of road surface, how good are my tires, what are the weather conditions like, what are the traffic conditions like, and you're going to integrate and differentiate both in the lay sense of those terms and in the mathematical sense, what's going on, and you're going to make a decision as to whether it's safe to go or not. So you see from the two happy, smiley cartoon faces there, if your perception is that it's good and the reality underlying that is it's good, okay, happy, smiley. Conversely, bad perception, bad reality, okay, that's good. Let's look at those other two corners, though. If your perception or belief is that it is not safe to go and the reality is it would have been, you're making what's called a type 1 error. So what's going to downflow from that if you make that kind of mistake? Well, you're going to wait another 20 seconds before you cross the traffic, right? On the other hand, if your perception or belief is that it was safe to go and it wasn't, and you proceed on that, well, bad things are going to happen. In the reliability world, we call that situation margin. So what you're looking at there is, what kind of margin do you have for those risks that you're going to undertake? We like to have margin. Margin is good. Too much margin is expensive. Not enough margin can be disastrous. So I talked earlier about acceleration factors and higher temperatures creating higher failure rates. For most materials, processes, and designs, that's true. There's an equation called the Arrhenius equation that we in the reliability world use to develop those acceleration factors from tests. However, there are also a number of non-trivial situations that are driven by inverse Arrhenius relationships. And largely these are mechanical kinds of things, latches, switches, things like that. But there's also an inverse Arrhenius relationship inside CMOS semiconductors. So we'll talk a little bit more about that in a subsequent slide. So in reality, what you're looking at there is a composite failure rate of both failures that happen more often at higher temperatures and failures that are more prone to happen at lower temperatures. So for those of us that have worked in the industry for a while, you've got all kinds of industry standards that we're familiar with and use. So let's say you're working around your house and you're going to build or rebuild a deck. One of the first things you're going to do is go to your city or county office, and get all the standards that are required, the building codes that you're going to be working with, and it's going to tell you things like, nailing schedules and joists and spans and all that kind of stuff, and you're going to build it to that standard. So this was an unfortunate situation that occurred a few years back at Senior Skip Day, where a bunch of seniors took the day off, and they're all happily celebrating. You can see some of the high school seniors there lifting their adult beverage that they probably shouldn't have been consuming, and they were dancing and having a good time. So there was a failure. You can see the deck kind of beginning its collapse there before, and then the after picture shows what happened. Mercifully there were no fatalities, or I wouldn't be showing this. But so what happened here? It was built to standard, and yet it failed. So the underlying supposition behind those building code standards are that the loads on the deck are going to be static loads. That is, they're just going to be dead weights of people on the deck or other things on the deck. They do not take into account dynamic loads, that is, people moving and dancing, nor do they take into account what's called as reasonably foreseeable misuse. So this is a legal term that we as design engineers are required to operate to, that we need to have our designs tailored not only towards the intended use, but also legally foreseeable misuse. So in the simulation world that we work at in Ansys, we have a lot of really excellent simulation tools that are available. So I like to kind of tee this up in terms of a catchy little phrase that I'll offer for your consideration, and that is rules versus tools. So design rules are great, they're necessary, but they're not always sufficient. And that's where simulation comes into play. One of the areas that I like to look at frequently is, because so much of it is available in the public domain, are all the air safety improvements that have gone into effect in commercial aviation over the decades. So some years ago, my wife and I were watching an old movie, and you got an aircraft that's a 4-engine propeller reciprocating engine aircraft that's flying from Hawaii to San Francisco, and one of the engines fails, and vibration is so extreme it dislodges the engine from its engine mounts and drops down into the airstream, creating a lot of drag. And now the question is, are we going to make it to San Francisco or not? And of course, there's a lot of drama in the movie. We're beyond the point of no return, and John Wayne, the hero, who's the captain of the aircraft, organizes a bucket brigade of the passengers to get down below in the cargo hold and handle all of the luggage out, individual, one piece of luggage at a time, and he heroically holds open the door to the aircraft, and they're tossing the luggage out, and they do make it back safely. So what was kind of interesting to me as a reliability professional was what was shown in that film was a very plausible thing that took place in commercial aviation back in the late 40s and early 50s. There were a lot of accidents of that and other similar natures that resulted in airplanes crashing and lives being lost. So what we're looking at here is a graph that the FAA put out a few years back for all Part 121 operations. So that's basically commercial aviation. So those are planes that those of us who travel by air, you see what happened there in the early 50s. A huge safety improvement, largely attributable to instrumentation landing systems. Then subsequent to that, there were more positive controls placed on the movement of commercial aircraft. They all had to fly under instrument flight rules. So there was distance measuring equipment and vertical omni range and those kinds of things. And then later on, precision approach. And then subsequent to that, ground proximity warnings, which I worked on, and area navigation and the TCAS terminal control around airports. And with each subsequent change, you could see that the accident rates continued to go down and down and down. And some of this was offered also to general aviation, but general aviation continued to be a little more dangerous than commercial aviation. I had a personal situation that happened to me that resulted in a friend of mine making a fatal mistake. So he and his wife are going to be flying from the Bellevue Airport in Washington State down to Las Vegas. A friend of theirs was going with them. That friend had much more experience. There was low-lying fog around that Bellevue Airport, which was located next to Interstate 90. The friend took off and made it across the highway and was up in the air and radioed back and said, yeah, okay, you can make it too. I made it. So my friend and his wife took off and they didn't make it. They crashed into the tops of trees that were on the other side of the interstate. So there's one of those situations of alpha beta risk, right? And how much margin? So the first airplane that went, how much did they miss those trees by? Was it 20 feet? Was it 1 foot? Obviously, they had more margin than the second aircraft that took off. So that's an example of a decision where you don't know how much margin you have. One of the things I really like doing, working for DFR Solutions and now Ansys, is having the opportunity to go out and travel around domestically and internationally and talk to clients and customers and see how they are using our services and tools. I had a great experience here about 5 years ago talking to an industrial control customer who had some field failures of a particular relay on a board that had a cracked solder joint. And that's what encouraged him to reach out to us and acquire our Sherlock reliability assessment tool that used reliability physics to try to predict those solder joints. And so we worked with them and got them to use that software package. And it not only predicted that relay was going to fail, but it predicted the actual pin on the relay. So a few years after that, there was a commercial aircraft that had an accident and landed in the ocean. All crew and passengers were lost. As I was looking to the publicly available report that came out later, my heart kind of sank because this circuit board was so close to that circuit board of the industrial control customer that I talked to just a few years before that. Now, if you look closely here at the board, what you'll see is there are a lot of heavy steel relays located over on the left-hand side and towards the center of this board. And yet the board is only supported on the four corners. You can see the standoffs there. So this circuit board and the rest of the boards and designs of that particular module all met the standards. And yet, because like the deck that I talked about earlier, didn't take into account the long-term effects of vibration, the solder joint cracked and failed. So, as is usually the case with these kinds of incidents, there are multiple causes going on. So one thing I want to mention and offer some emphasis on is when you have a return product and it comes back and you test it and you can't find the failure, there's a tendency to ascribe that to NTF, no trouble found. And what I've emphasized with the people that I've worked with throughout my career is, let's not think about it that way. Let's not conceptualize it as no trouble found. Let's conceptualize it and talk about it as trouble not found. And that was the situation with this particular rudder limit control piece of avionics, that there was an intermittent that was caused by this cracking solder joint on the relay. And this had been rejected and tested several times. It was taken off the aircraft, sent into the avionics shop. It passed, so NTF, let's put it back into service again. So the particular accident that resulted from this, there were multiple causes. There was a lot of weather disturbances going on in the Pacific Ocean at the time. Unfortunately, the captain of that aircraft executed an action that was not part of the flight manual or instructions. So he had been talking to one of the ground support avionics people, and they told him that, one thing that we do here on the ground is when we have things that operate and don't work and start to work again, kind of like you do with your Windows computer, right? You reboot. And that's what we do here on the ground. We remove the power and reapply the power to the aircraft avionics. That resets everything, and then things start working again. Unfortunately, the captain decided to do that in flight. Now, the flight control avionics for all aircraft are very redundant. In this particular aircraft, it was a triple redundant system. But what happened when he did that in flight, let's pull the circuit breaker and reset everything, is that the voting circuitry couldn't vote anymore, because what it did was it looked at the triple redundant signals and systems, and if one disagreed, then it discounted that, stayed with the two that did agree, and that allowed you to continue flying. However, what happened when he cycled the power to all the avionics on board is that nothing agreed anymore. So the voting system failed. That resorted the aircraft to full manual control. At the same time, they were fighting all this weather phenomenon. So like I said, it's a very complex thing. But at the heart, had there not been this fractured solder joint, had there not been this intermittent, we wouldn't have had that failure and subsequent loss of aircraft crew and passengers. So this is a reliability model that I use in almost every presentation that I've given here for the last several years. So what we're looking at here in terms of reliability, on the vertical axis are environmental stresses. So this would be shock, drop, vibration, high temperature, low temperature, temperature changes, going up and down, humidity, all of those environmental stresses that cause failures in electronics. And along the horizontal axis, what we're looking at is product lifetime. So if you look, the upper right-hand quadrant there, high environmental stresses, long product lifetime. So these are, satellites, commercial military aircraft, auto safety, those kinds of things. In the lower left-hand quadrant, we've got things like toys, cell phones, laptops, video games, those kinds of products. So the products in the lower left quadrant tend to live their lives in more benign environments and have shorter product lifetimes. So there's a couple things going on here that I'll call your attention to. So the arrow that you see there, historical technology flow over the last approximately 100 years. So all of these design rules and the processes and materials and the components and those kinds of things were, in the old days, largely developed in this upper right-hand quadrant. And if there was anything we in the electronics industry were good at, faster, better, cheaper kind of stuff, right, was figuring out how to take those expensive yet very highly reliable materials, processes, components, designs, and applying them in larger and larger quantity productions to more civilian kinds of applications and uses. There was a lot of margin that was built in to that, and so that was pretty successful. But today, what we're looking at is a lot of today's technologies, if not the majority of them, are being developed for use in that lower left-hand quadrant. So what we as design and reliability engineers are faced with is taking those materials, processes, components, and designs that were intended for use in that lower left-hand quadrant and dragging them up into the upper right-hand quadrant. So that's a much more difficult set of processes. So if you haven't seen that three-letter acronym before, RCG, it stands for Revenue Center of Gravity. So in the old days, the revenue center of gravity was very well placed in that upper right-hand quadrant. So you had companies that were producing the materials and components, doing so to meet those requirements. And today, that's not the case. The revenue center of gravity has shifted down into that lower left-hand quadrant. So we need to pay a lot more attention to what's going on there, so we can make those applications more successful. So again, a continuation of the conceptual product space and technology flow model that I developed and am now offering for your consideration and use. So one of the things that people are very much aware of is what has happened in that transition. In the old days, we were dealing with much larger geometry. So there were bigger parts, larger solder joints. Things were more spaced out, and today there are much smaller geometry. So as designers, we're all pretty much familiar with that. So one thing that is a much smaller geometry now than it used to be in the past is something that as designers we may not be aware of because it resides in circuit board production. So one of the things that is much smaller now than it used to be are the solder spheres. So as a designer, we may or may not be aware of the size of the solder paste particles that are being used to produce the boards that we've designed. So as the parts have gone smaller, as the pads have gotten smaller, the traces have gotten smaller, more and more manufacturers are using smaller and smaller solder paste particles. And the way that this works into reliability is that as you go to smaller and smaller particles, you have more and more surface area, which means that the fluxes that your manufacturing folks are using have to be more active fluxes to keep the oxygen in the air away from the solder joints so that the solder paste can melt and form a nice, good intermetallic bond between your components and your pads on the board. So that means, as I said, more active fluxes, which means we have to pay more attention to what's going on in terms of cleanliness. A couple years ago, I was offered the opportunity to make the keynote address at the SMTA IPC Cleaning and Coating Conference. And the topic I was asked to address is the reliability of cleanliness effects in the medical device industry. Now, when I started my career in medical devices about 20 years ago, we were very much captured by the move fast and break things approach to reliability. And it worked pretty well in those days. We had a medical device that was used by paramedics out in the field, which is essentially a very high stress environment. It's uncontrolled in terms of humidity, temperature cycling, shock drop vibration, that sort of thing. So we wanted to make our new model extremely reliable, very tough, very rugged. So using that move fast and break things kind of approach, what we did is we did both in-lab tests, but we also did what we called was the salesperson's toss. So we took this pre-hospital medical device and tossed it up into the air, and it would arc over and land on the floor and clatter, clatter, clatter. And then we'd open the thing up and see what broke and change the design, put in a standoff or two, use some more encapsulation, use some more epoxy, test, analyze, fix, test, analyze, fix. The result of that was an extremely popular, very reliable, very rugged product. And today, we can't do that kind of thing. There's more competition in that and in other industries, and that's what's leading to pervasive modeling and simulation, where you can develop mathematical models of what's going on both statically and dynamically, and do that subsequent cycles of model and remodel before you actually go out and do physical testing. So I developed what I call this medical model of reliability, and I kind of call that the gold standard. So there's three big aspects to that: knowledge, decision, and actions. How we know things. So in medicine, that's anatomy, physiology, that sort of thing. Decisions, when you go into your healthcare practitioner, you'll get, signs, symptoms, imaging, whether that's in X-ray or acoustic, chemistry, you'll do lab tests, that kind of thing. And then the actions that your healthcare practitioner will take will follow along, this kind of, diagnosis, prognosis, consultation, treatment, follow-up plan, all that kind of stuff. And I call this the gold standard because it gives a lot of insight into what's going on. There are analogies that you can draw in each one of those areas as to how we're doing our designs and how we're doing our manufacturing. So anatomy, that would be how the designs are put together. Physiology, that would be, how they're working. Signs, symptoms, imaging, that's the kind of stuff that we do in a failure analysis lab, so on and so forth. So if you think about it and conceptualize it in those kinds of ways, you get a lot of insight, which means you have foresight as opposed to hindsight. So I talked earlier about margin and how much margin do you have. So when we're using a low solids flux at a no clean process, there's a lot of opportunity for things to go wrong there. If we look at this particular graphic, what we're seeing is a circuit board with some traces that I've labeled anode and cathode. So plus on the left, minus on the right. So you have an electric field that's being formed. But what you may not be aware of is that even under low humidity environments, there are monolayers of water that are on the surface of your board material. And these little rascals, as I've shown here in the picture, they kind of line up like little magnets under the effects of that electrical field. So even if you have what you think to be a dry situation, when you get down and look at it microscopically, you've actually got liquid water on the surface of that board. So you can have a situation that you can have electrochemical migration taking place or leakage paths that are being formed. So the kind of key takeaway there is you don't really know how much margin you've got. And if you think about this in terms of alpha beta risk, whether you're going to take off with that plane or whether you're not going to take off with that plane, calls for some circumspection when it comes to the decision that you're making, whether you're going to clean or not. So a few years ago, I was at an electronics materials conference in Europe. and I ran into Barry Dunn, who I was familiar with his work. He did a lot of work in tin whiskers and that sort of thing when he was working at the European Space Agency, and he gave me a gold nugget. And so I'd like to offer that up for your consideration, use, and application. And what he had done, he and his team, when he was at the European Space Agency, they were trying to quantify cleaning effectiveness. So we all know when it comes to cleaning boards that it's easier to clean under components where you have a lot of spacing. But what absolutely stunned me was that what they had shown was that the cleaning effectiveness goes up as a function of the fourth power of the spacing. So for those of us that engineers that were used to working with math and mathematical models, we know intuitively what that fourth power means. But the folks that we're talking to in other organizations and other disciplines may not. So what I've offered for you here is you look at the one where it's a square function that's a little bit of a ramp, cubic function goes up, and the fourth power goes up even much more dramatically. So the implications of that is when you're designing your circuit boards and you're selecting your components, for cleaning purposes, you need to fight for every little micron that you can to get better and better spacing so that your cleaning effectiveness is enhanced instead of degraded. So some work that was done by Bev Christian and his team at Research in Motion and BlackBerry that they published a few years ago, where they looked at component cleanliness. So in previous episodes of the Reliability Matters podcast, the guests have talked about, one of the things that you need to be thinking about in terms of cleanliness and cleaning is if you make a decision not to clean, you're making a decision to leave all the contaminants in place that your boards and components arrive with. And so what they found out in their research is there were significant shortcomings in component cleanliness, the most serious of which was methane sulfonic acid, or MSA. So that's a widely used chemical compound that's used in plating, particularly tin plating, for the leads and pads of components. And the reason that chemical is used is it ionizes extremely well. And so if your component manufacturer is not doing a good job of cleaning and rinsing, you're going to find that MSA, methane sulfonic acid, as an unfortunate remnant on your components. And we have seen this. This has been reported in more than one paper that's been written about component cleanliness. So the last thing that I'd like to mention about component cleanliness and circuit boards and cleaning, there was some work that was done by Phil Isaacs and his team at IBM. There was a series of 3 papers that were presented at the SMTA Microelectronics Conference over the past few years. And what they showed conclusively is that it's a myth that there is that 3-stage step of so-called activation of evaporation, polymerization, and encapsulation. So doing a differential scanning calorimetry, they could not find any evidence at all that second step was taking place. So the implication for that is that there is nothing that goes on in that reflow process that makes those residues benign. What makes them benign is that third step of encapsulation. So what they showed conclusively is you need to process your boards so that you have a benign glassy state on the residue of those low solids or no clean fluxes. Those are good resources. What they've showed conclusively was that it's not enough to have the temperature ramp on your reflow get to that high temperature. So if you have components, QFN components as an example, ferrite filter components as another, where the outgassing and temperature processing does not reach into the interior of the components, that the fluxes on the outside edges tend to seal off the evaporation from the inside. So you're left with a gloopy, goopy flux residue mess that has not been fully processed. So the current state of thinking there is let's not talk about this in terms of activation. Let's talk about it in terms of passivation. So talk a little bit about reliability physics and the CMOS failure mechanism. There was a Reliability Matters podcast here a few weeks back that sort of introduced the topic of CMOS failures. We at Ansys have done a lot of work on this. There was an IEEE Spectrum article that came out a few years ago that proposed, maybe it's even time to consider what they called a silicon odometer. So here are the four major mechanisms: electromigration, oxide breakdown, hot carriers, and bias temperature instabilities, bathtub curve, and you break it out into the kinds of failures that are going on inside CMOS. Here's what it kind of looks like. So you have those four things that I talked about here just a moment ago, all adding up. Now, I mentioned earlier that one of these is an inverse Arrhenius equation failure mechanism when you go out and model it. And that's the hot carrier injection. And so if you're going to do testing for CMOS, it's not the case that high temperatures will accelerate all of those mechanisms. So that's a situation where modeling is a much more appropriate thing to use, so that you capture both those Arrhenius and inverse Arrhenius failure mechanisms. So we're all familiar with, as I said earlier, decreasing geometries that takes place in semiconductors as well. You have smaller and smaller process nodes. I was at the International Reliability Physics Conference here a couple years ago. Got this great graphic that you're seeing on the right-hand side of your screen there. So the established simulation paradigm looks at those gates in terms of solid structures. But what we're seeing now is you get down to smaller and smaller gates, down to 9 nanometers and smaller. You're actually at the point where individual atoms are at play in the operation in the failure. So that I think that's a pretty nice little graphic that shows that you get down to those smaller gate geometries, and as the author of this paper shows, your typical gate geometries are in the terms of 30 by 30 by 30 atoms, for crying out loud. I mean, that's just absolutely stunning. So also at that reliability physics conference, there was a paper presented that showed what radiation looks like for increasing altitude. So as you can see there, you're down at sea level. Relative radiation flux densities are small. You go up higher and higher in altitude, you get more and more cosmic radiation impinging on your semiconductors. The smaller and smaller those semiconductor features are, the more susceptible they are to that ionizing radiation. So you'll notice here that this stops at 4,000 meters, which is, as I remember, is like, I don't know, 10 or 12,000 feet, something like that. But what are the altitudes that commercial and military aircraft fly out? Well, that's 35, 40,000 feet. So you can see from the shape of that curve that as you get up to those kinds of operational altitudes, you have increasingly higher rates of radiation impingement that can affect your CMOS elements. So here was a presentation that was made at the SMTA Microelectronics Conference in 2017. So again, when things go wrong in commercial aircraft, there's never a single cause. There are multiple causes. But fundamentally, what happened in this particular situation was most likely attributable to radiation at altitude. So there was an upset, not terribly dissimilar to the one that I talked about earlier with the power cycling. In this case, the upset led to the autopilots disengaging and followed by two uncommanded pitch down maneuvers that were very violent. So it knocked the passengers around. You can see holes there in the overhead structures with panels popping out and that kind of thing. So again, here's a situation where modeling can come to the fore. DFR Ansys is now working with the Defense Threat Reduction Agency on being able to model radiation effects at CMOS, and we'll be incorporating that into our pervasive simulation software here shortly. So that's it. Thanks for your attention. So I hope we've passed along some interesting things here that people can take advantage of.
Doc, thank you very much. That was exceptionally informative. And I have to say, you made me quite happy because of all of your aviation analogies and comparisons. I'm an aviation geek. And do you fly? Are you a pilot?
No, I had to give up my my certification for medical reasons. But
but you used to fly.
Yes.
You've got that. I can tell. One pilot to another. I'm also a pilot, although I'm not current anymore. But I stopped flying a lot of years ago. But I live near Los Angeles, and being in the sky is a whole lot of fun. But being in the sky in a super controlled airspace is no fun. It's work, right? So I remember once
working in that you were in that TCAS environment then around
absolutely
airports. Yeah,
absolutely. And the first thing I would do is get out of Dodge. I would take off out of our local airport and fly to an area that's not controlled. And I do remember once I had no radar following, and I remember coming so close to another plane in the sky that I could recognize the pilot. I mean, it was seared into my head. I could see the look of fright on his face and my face. And then my training kicked in. They say, if it looks like you're going to hit another plane, the best thing is not to do anything, because what you don't want to do is increase your envelope. You don't want to, chances are, big sky rule. Chances are there's a lot of sky, there's not a lot of plane. You're not going to hit anybody. But that was a test of the big sky rule. So I'm happy to, that was kind of one of my last flights. But anyway.
It's a wise man who knows his limits.
Exactly. Although I'm still the one person, whenever I hear something in the air, I'm the guy looking up, and, I can tell them what type of aircraft it is, and I can spot the livery and tell you what airline it is. I'm just that geek. But anyway, a couple of takeaways for me that I really appreciated. One is kind of the movement of the letters NTF to TNF. I think that is a much better way to look at it, because clearly if something was returned back to the factory because it wasn't working, there is trouble. So I do love the idea of trouble not found as opposed to no trouble found. In my webinars and stuff like that, I have another acronym whenever there's NTF, and I call it WTF, because they can't duplicate the problem. That is a test engineer's worst nightmare is they can't duplicate it. The problem exists outside of the lab, but it doesn't exist inside the lab.
And that's especially the case with avionics. The one thing you don't want to do is add to the air crew's stress and add to their uncertainty and concern. That's a bad situation.
Sure, they have enough to do up there. Absolutely. And then the last kind of takeaway, I'll throw in a little anecdote. You were talking about flux activation, encapsulation, things like that. Our friends at Foresight Analytical Laboratories in Kokomo, Indiana, recently did some testing, and they ran boards. I think they were B-52 boards, test boards. They ran these test boards at the proper peak temperature for the materials they were using, which was 250 degrees C, and then extracted whatever residues there was from under various components, subjected them to ion chromatography, established the baseline, and it was a no clean flux. And then they lowered the reflow temperature by 10 degrees, 4%, 10 degrees, and then ran the same tests and found increases in detectable contamination up to 600% under various components. 10 degrees, right? So most reflow profiles are pretty well under control. But if one is running no clean and maybe your profiling maybe your oven's not quite that good, maybe your vents are dirty, whatever could cause that reflow temperature to be off a little bit, they're running no clean and not cleaning under the kind of promise that the residues are benign, but all it takes is a 4% variance in peak reflow temperature, and that argument is out the window. So it was just an interesting look at that,
Well, that gets back to the concept of margin. If you're in a situation where you don't absolutely positively know how much margin you have, that's a reason for being a little more circumspect, for being a little more conservative, for doing a good job of cleaning, rinsing, and drying.
Right. I'm glad you said rinsing and drying. Drying, most people forget about. But as you well know, in your Ansys world and reliability world, that CAF is a big issue. Conductive anodic filament is a measurable issue in our industry, and you can't clean your way out of a CAF problem, but you can certainly dry your way, at least for a while, out of a CAF problem. So I think drying is just as important. All are wash, rinse, dry are important. Rinse is probably the most important. Dry certainly is up there. It's often overlooked. Doc Brown, thank you so much for being my guest today. This was exceptionally informative, and it's a departure from the way we normally do these podcasts. Normally it's question answer, it's conversation, but I really appreciate the whole presentation. That was amazing. For my audience who are in their cars listening to this on Apple Podcasts or Google Podcasts or Spotify, and are experiencing a little FOMO, a little fear of missing out from not seeing the slides, feel free to go onto our Reliability Matters YouTube channel, and this presentation, complete with Doc Brown slides, will be on there. So you'll be able to see what Doc was talking about. Doc, thank you so much. I hope you stay well, stay healthy in these crazy times. Hopefully, you're probably a bit grounded like everyone else, right? Not traveling too much.
Unpleasantly so, but we'll get out of that this year. We're all on the list to get our inoculations and vaccinations, and so hopefully we'll be able to put that behind us.
Yeah, it's funny that when I travel a lot, as you do, as I first kind of locked down, it was nice. It was nice not to have to get on an airplane, not to have to get up early and find parking at the airport and all the things we do, right? And now I kind of miss even the worst days of travel. I'm starting to miss that now, right? I'm starting to miss crowded airplanes next to smelly people, So I'm looking forward to going back to that level of normalcy. Well, thanks again for being my guest, Doc. You're a wealth of information, and thanks for making this available for generations of engineers to come. I really appreciate it.
It was a great opportunity, Mike.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, or virtually wherever you get your podcasts. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks for your questions and episode suggestions. Please keep them coming. Send them to my email address, mike@mikeconrad.com. That's Conrad with a K. Once again, thanks for listening. Stay safe, stay healthy, and stay happy. And most importantly, keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.